In today's first warm-up, we are going to practice factoring trinomials. So what we want you to do is hit pause on the video, factor each trinomial if possible, watch out for signs, then when you're finished, hit play and we'll discuss our factoring. Okay, so let's look at this. The first thing I notice is that each of these trinomials are what we call quadratic trinomials. That means that they are in the form ax squared plus bx plus c. Now, the other thing I notice is that they all have a leading coefficient of 1. So what that means really is that we're just dealing with x squared plus bx plus c. And so that makes this easier to factor than if a was not 1. Because what we have to do is we have to find two factors that multiply to make the c value, but also add to make the b value. So let's get started. I have t squared minus 4t minus 21. So when I'm setting up my parentheses, I know the first term of each parentheses is going to be t, because t times t is t squared. Now, I need to find two numbers that multiply to make negative 21, but also add to make negative 4. So let's think about our factors of 21. We have 1 and 21, and one of them's got to be negative. So we're either going to get 20 or negative 20. So when we add them, so that wouldn't work. Let's try 3 and 7. Well, if I made one of them negative, 3 or 7, doesn't matter, I'd get negative 21. But also if one of them's negative and I add them, I can manipulate that so that I could get negative 4. Okay, so we're going to put 3 and 7. Now, because I want it to be a negative 4, I'm going to make the 7 negative and the 3 positive, because we can check that, because t times t gives me t squared. Okay, that works. Let's try the O and the I. Negative 7t plus 3t is negative 4t. Okay, that works. And then lastly, 3 times negative 7 is negative 21. So we can always multiply those back together, and if we get the original trinomial, we know we've gotten the right answer. Let's move on to the next one. X squared plus 13x plus 12. Well, again, same reasoning. I know that the first term is going to be x because x times x is x squared. So now I need two numbers that multiply to make positive 12 that also add to make positive 13. So here's another thing. I noticed that since both symbols in the trinomial are addition, then that means that the signs are both going to be plus, because we want a positive 12 and a positive 13. So the only way to get those is if both factors are positive. So let's talk about factors of 12. Well, 1 and 12, if I multiply them, that makes 12. But 1 and 12 also add to make 13. So again, I could check that x squared, and then 12x and 1x make 13x, and then 1 times 12 is 12. Okay, let's move on. X squared minus 10x plus 24. Okay, so let's talk about that. Again, same reasoning. My first term is x. I need two numbers that multiply to make positive 24, but also add to make negative 10. Now I notice that this is plus and the b is negative. So 24 is positive, but b is negative. Well, the only way to find two numbers that multiply to make positive 24, but also add to make negative 10 is if both factors are negative, because a negative times a negative is a positive, but a negative plus a negative is still negative. So factors of 24. Well, there's 1 and 24, 25, that wouldn't work. 2 and 12, well, that would make 14, so that's not going to work. 3 and 8, That makes 11. We're getting closer, but we're still not there. And 4 and 6? Yes, because 4 and 6, they multiply to make 24, but they also add to make negative 10. All right, last problem. X squared plus 3x minus 18. Okay, well, it's an x squared again, so we know that our first term in each parentheses is going to be x. Now, I need two numbers that multiply to make negative 18, but also add to make positive 3. Well, there's 1 and 18. One of them's got to be negative, so that would either be 17 or negative 17. Okay, that's not going to work. 2 and 9, well, one of them's negative. That's either going to be 7 or negative 7. 3 and 6, well, 3 and 6, if one of them's negative, that'll multiply to make negative 18. And if one of them's negative, it'll either be positive 3 or negative 3. That would work. So let's do 3 and 6, because that multiplies to make negative 18, but one of them has to be negative. So I look to my b-value. Well, the only way to get a positive 3 when I add them is to make the 6 positive and the 3 negative, because negative 3 times 6 is negative 18. However, positive 6 plus negative 3 makes positive 3. So we're done factoring. That leads us directly into our SAT prep question of the day. If a squared plus 14a equals 51 and a is greater than 0, what is the value of a plus 7? So what I want you to do here is hit pause, try it on your own, and then when you're ready, hit play and see our explanation. Okay, well, the first thing I see here is a squared plus 14a equals 51. That's a quadratic. And to solve a quadratic, it has to equal 0. So first thing I'm going to do is subtract 51 from each side to make it a squared plus 14a minus 51 equals 0. Now I have to find two numbers that multiply to make negative 51, but also add to make 14. So there's 1 and 51, no chances there. 2 doesn't go into 51, so not a factor. 3 goes into 51 17 times. Woo! And I can, since it's negative, I can manipulate it so that I get a positive 14. So to get a positive 14, it's going to have to be a positive 17, but a negative 3. So I say a plus 17 times a minus 3 equals 0. And then if you remember from Algebra 1, I said each one equal to 0, and I solve for a. So a plus 17 equals 0, meaning it's negative 17. And then a minus 3 equals 0, that's a equals 3. Okay, so we've got two solutions here in our solution set. We've got a negative 17 and a positive 3. But go back to the other criteria. A has to be greater than or equal to 0. So that means 17 doesn't work. Excuse me, negative 17 doesn't work because negative 17 isn't greater than 0. So the only one that works out of that solution set that meets that criteria is a equals 3. Well, fantastic, but we're still not quite done. We then have to take that a and we plug it into a plus 7. So 3 plus 7 is 10. So the solution to this problem is 10. All right, let's start with our lesson today. We are working on notes 2.2, Systems of Inequalities and Linear Programming. Now, you've probably done a lot of this in Algebra 1, definitely the system of inequalities. Linear programming may be a little bit different, so that's going to be pretty much the brunt of our lesson, if you will, the majority of our lesson, but we are going to review some systems of inequalities because you will need to use that knowledge to assist you with linear programming. Now, don't let the term linear programming scare you. All it is it's a word problem based on systems. So we're going to talk about some vocabulary, we're going to talk about how we tackle those problems, and then we'll move on. Okay, let's look at our first example. A couple things I want to talk about with you before we begin this example. And the first thing is we need to talk about, is the line solid or dashed? And do I shade above or below? So you're going to use a solid line if it's greater than or equal to or less than or equal to. And remember, we read our inequalities left to right, much like we read a book. So if it's greater than or equal to or less than or equal to, that means that my solution could lie on the line, but it could also lie in the shading. So your solution, any point on that line or the shading, would make your inequality true. However, we use a dotted or dashed. Dotted, dashed for this purpose means the same thing if it's strictly greater than or strictly less than, because strictly greater than or strictly less than means that my solution only lies in the shading. We cannot count the line. So solid lines and dotted lines are much like, if you think back to the simple inequalities, the open circle and the closed circle. So if you'd use a closed circle, you're going to use a solid line. If you would have used an open circle, you're going to use a dotted or dashed line. Another way I like to help me remember it is, if it's got a solid line under it, then we're going to use a solid line. No solid line under the inequality symbol, we use the dotted or dashed line. Now, let's talk about how we determine above and below on a line. Okay, and it's really quite the same philosophy if it's a positive slope line or a negative slope line. So in terms of above, I always like to think about if I have a guy and he's walking up a hill or down a hill. If he is walking upright, that means above because he is above the ground. Okay, so again, same idea. If he's walking above the ground, above the hill, that's above. However, if he is walking upside down, kind of like Spider-Man, that is below the line. So if he's having to walk upside down to stay attached to the hill, then he's walking below. If he's walking upright, that's above. If he's walking upside down, that's below. The other thing, with a horizontal line, it's pretty easy to determine if it's above or below. If it's a vertical line, less than is left, less than left, greater than would be to the right. Okay, let's start this example. So I'm going to erase all my little guys walking uphill and downhill. Okay, so on our first example, we are going to graph y is less than or equal to 1/2 x. So remember, that's the same as 1/2 x plus 0. So that means I'm going to start at the y-intercept of 0, 0. I'm going to go up 1 over 2, up 1 over 2. I'm going to return back to 0, 0, and go down 1, left 2, down 1, left 2. Now, I also know it's going to be a solid line because it's or equal to. So there's my line. On our next example, we're going to graph y is greater than or equal to x minus 1. That means I'm going to start at 0, negative 1, and then I'm going to go up 1 over 1, up 1 over 1. I'm going to return back to 0, negative 1, and then go down 1, left 1, down 1, left 1. And in this case, my line is also going to be solid. So it looks like that. Now you may be wondering, why aren't you shading? Here's why. I always save my shading till the end because I don't want to try to be shading and graphing at the same time. So I always save my shading to the end. Let's look at our last equation they want us, or inequality that they want us to graph. y is greater than or equal to -2. Well, there's no x there, so that means it's going to be a horizontal line going through y is equal to -2. And it's going to be solid as well. Now, when we talk about shading, you may wonder, okay, that's a lot to decide. So I take each piece individually. So the first one is less than, so that means I'm going to shade below. Okay, the next line is greater than. So I'm going to take it and I'm going to shade above. And then lastly, y is greater than or equal to -2. I'm going to shade above. So where these three colors overlap is right there in that triangular region. Okay, and you may be asking, do I have to do all the shading, or can I just visualize where it's going to be and put the shading there? That is perfectly fine. You can do 3 separate shadings, or you can visualize where they'll all overlap. Okay, let's look at our next one. We have y is less than or equal to +4. Again, no x, so that's going to be a horizontal line. Again, and it's solid because it's less than or equal to. Let's look at our next one. Y is greater than x minus 1. So that means I'm going to start at -1 on the y-axis. I'm going to go up 1 over 1, up 1 over 1, go back to -1, and then go down 1, left 1, down 1, left 1. Now, this line is going to be dashed because there is no or equal to. It's strictly greater than. So there's that line. All right, last one. Y is greater than -x plus 1. So this means I'm going to start at -1, start at +1, start at +1 on the y-axis. I'm going to go down 1, right 1, down 1, right 1. I'll return back to +1 on the y-axis, and I'll go up 1, left 1, up 1, left 1. Now, this line is also going to be dashed because there's no or equal to. Now let's talk about shading. Okay, if we talk about shading, it's less than, the y is less than or equal to 4. It is greater than x minus 1. So that is above. And then lastly, it's greater than -x plus 1. So that's here. Now where they overlap is right there in that triangle. Again, you don't have to do all of the separate markings. I apologize for that. You can strictly go by the overlap there. You don't have to do these separate markings. Let's look at example 3. We're going to be talking about linear inequalities in one variable. So the problem is that Baxter wants to buy a moped to go to Kitty College. And yes, I actually found a picture on Google of a cat riding a moped. But anyways, so he wants to buy a moped to go to Kitty College. He has saved $345 thus far. His weekly expenses are $125 per week, but his income is $200 per week. How many weeks will it take to earn him the $1,999 needed for his moped? So let's talk about what we've got going on here. So he has saved $345 so far. Now that's not per week, that's how much he's starting with. He has saved $345 up to this point. The next thing it tells us is that his weekly expenses are $125 per week. This part's critical. $125 per week. Now, expenses, that means subtraction. Okay, subtraction. Then it goes on to say his income is $200 per week. And again, here we go, 200 per week. Now, income means that I'm adding to my savings. Expenses mean I'm subtracting. Income means I'm adding. So we come up with the following inequality. Now, we're going to have $345. We're going to subtract 125 per week. So per week gets a variable. And then we're going to add 200 per week. It then goes on to say, how many weeks will it take him to earn the $1,999? So we have to decide, is that going to be less than or is it going to be greater than? So we need this 345 minus expenses per week plus income per week. We need that to be greater than or equal to $1,999, because if it's less than, then that means he won't earn it. He won't earn what he needs to get his moped. So we come up with this equation, or excuse me, inequality. 345, because that's what we started with, we're going to subtract 125 per week. We're going to add 200 per week. And again, that amount needs to be greater than or equal to $1,999. Now we know we're going to combine like terms there. So I end up with 345 plus 75W is greater than or equal to 1,999. And then we just solve. We subtract 345 from both sides. And that leaves me with 75W is greater than or equal to $1,654. We then divide by 75. And we find out that he's going to need 22 remainder 4 weeks. So you could do 22.7 or you could write as 22 remainder 4. But we need whole weeks. How many weeks? So at 22 weeks, he's not going to have enough money because we'd have some like decimals left over. So in this case, we would say that he would need a total of 23 weeks to earn what he needed for his moped. Now, at 23 weeks, he's going to have more than $1,999, but that just means he can buy a kitty helmet for his little kitty head. All right, so it's going to take him 23 weeks to earn the required $1,999. Okay, let's look at example 4. Linear inequalities in 2 variables. All right, so Peyton's kitty soccer team is trying to make $6,372 for the team banquet. They are selling restaurant cards and stadium seats. They make a profit of $4.50 for each card and $6 for each seat. So what we're going to do is we're going to write an equation that models the situation. We're going to graph it and discuss what the intercepts mean. And then we're going to explain what must be sold to make the money and what do the coordinates below the graph represent. Okay, so first thing is we need to create, well, here's our axis. You'll notice I made the x-axis the cards and the y-axis the seats. And you'll notice that I'm counting by 500. So 500, 1,000, 1,500, etc. Now let's write an equation that models this situation. I made $4.50 for each card. $4.50 for each card. So I'm going to let C represent the cards. So $4.50 times the number of cards. Okay. And then it says $6 for each seat. So I'm going to let S represent the amount of seats I sell. So $6 times S represents the money I made by selling the seats. And then lastly, I know I need to make at least $6,372. So that's going to indicate a greater than or equal to 6,372. Because if it's less than, that means I would be okay making less. And that's not true. I need to make at least. So it needs to be equal to 6,372 or greater than. So this is how I come up with my inequality. Okay, so let's sub in 0 to find each intercept. So if I sub in 0 for S, then if I sub in 0 for S right here, okay, that and do $4.50 is greater than 6,372. That means that I would have to sell 1,416 cards. So by subbing in 0 for S, that means I didn't sell any seats. So if I don't sell seats, that means I am going to need to sell a minimum of 1,416 cards. Okay? Now let's talk about plugging in 0 for the cards. So if I plug in 0 for the cards, that means 6S is greater than or equal to 6,372. And that means that I would have to sell 1,062 if I sold only the seats. Okay, if I sell only the seats, I would have to sell 1,062 seats. So let's graph that. Now it's going to be a solid line because it's or equal to. Now you're probably wondering, why don't you extend that beyond that first quadrant? Here's the reason. Because in quadrants 2, 3, and 4, one or both of the quantities are negative, and we can't sell negative quantities. So we restrict it to be the first quadrant because that's where the quantities are all positive. Okay, so that's why we restrict it only to the first quadrant, because we want our quantities to be positive. So now let's talk about shading, okay? So if we look right here at this symbol, it needs to be greater than or equal to. So greater than or equal to is going to be represented by the area above the line. It's representative of the area above the line, okay? So that means that all the points on the line represent, so let's talk about our solutions. All the points on the line itself, so just these points right here, the points on the line represent what combination of cards and seats. So it's a combination. These represent combinations of cards and seats that I would need to sell to make exactly $6,372. The points in the shaded area, so the points in the shaded area right here, the points in the shaded area represent making more than the required amount. And then lastly, the points in the non-shaded area here, they represent where I would not make enough. Okay, so let's re-say that again. So the points on the line represent what I would need to sell, the combination of cards and seats that I would need to sell to make exactly that amount. The points above in the shading represent what I would need to, what I would not sell, but it represent the combination that would bring in more money. So points on the line, the combination that would give me exactly what I need. The points above the line represent making more, the combinations that make more than 6,372. And the points in the unshaded or below the line represent not making enough. So that's how we break down our analysis of that graph. All right, let's talk about linear programming. Linear programming is a method of finding a minimum or maximum value of a quantity given a set of constraints. So in a way, that example we did with the kitty soccer problem, that could be an example of linear programming if we had more data. Okay, so but we need to learn some vocabulary words because you're going to need them, because we're going to talk about what are your constraints, what is your feasible region, what are your vertices, so you need to understand what all these words mean going forward. So the first word we're going to look at is constraint. Constraints are restrictions on the variables of the function. So think back to that kitty soccer problem. If you remember, we talked about that we have to use the first quadrant because in quadrants 2, 3, and 4, that would place negative quantities on those products, and we can't sell negative quantities. So that might be restricting your data to the first quadrant. These could also be limits on time, money, and material. Like I only have 6 hours to prepare my materials, or I can only spend $600 on supplies, whatever. I only have 5 of these blankets to make, whatever, okay? These are going to be the inequalities or the boundaries of your graph. So that graph or that line that we graphed back on the kitty soccer problem, that would be a constraint, okay? So that would represent a boundary of what we're going to graph. So these constraints, they're going to produce the boundaries, the lines that we actually graph. The feasible region, this is going to contain the points that satisfy your constraints. Okay, so guys, feasible region is the shaded area. That's a fancy name for shaded area. Okay, again, this is all the points in the overlapping area. Okay, AKA shaded area. Then the vertices. The vertices are the corner points of your feasible region. So like if you think back to that triangle one we did where our shaded area was a triangle, your vertices would be the vertex or the angles of each. So it's going to be where your lines overlap. Okay. Now you're going to then take the vertices and you're going to sub them into the objective function to find the maximum or minimum. So the objective function. This models the quantity that you want to maximize or minimize. So a constraint, these are your boundaries. These are the lines you graph. They're limits. Then you do the shaded area, also known as the feasible region. Then you find the corner points. Where do my lines intersect? And then lastly, you take those corner points, those vertices, and you plug them in to the objective function. Now, quantities could be cost or profit. Here's the thing. You want to minimize cost. So if you're doing a cost equation or an inequality, you want to minimize cost. But you want to maximize profit. So if you're doing a cost objective function, you're finding the one that produces the smallest cost. If you're doing profit, you're going to find the corner points that give you the biggest answer or the biggest profit. Now, guys, if you do your linear programming with this order, there's a reason these words are written in this order. You should have no trouble. The first one is define your constraints, graph them. The second step is find the shaded area, do the feasible region. The vertices, those are the corner points of your feasible region, the corner points of the shape that's shaded in. And then lastly, you take those corner points and you plug them in to the objective function. So if you do the linear programming problems in this step, you're going to be just fine. All right, let's start here. Bella's Underwater Basket Weaving Club is selling quantities of snorkels and baskets, and they want to maximize their profit. Okay, so they give us the objective function right up here. So our profit is defined by making $6 off every set of snorkel and $15 off each basket. Okay, you will never, ever, ever, never, never, ever, never, ever graph the objective function. The objective function is what you're going to use to plug in. Okay, so let's talk about our constraints. In this problem, they gave us our constraints. We know that 2x plus 4y has to be less than or equal to 16. We know that 3x plus y needs to be less than or equal to 9. And then x is greater than or equal to 0 and y is greater than or equal to 0. Now, let's talk about these two quantities right here. We have to put those quantities into every linear programming problem because we are talking about quantities of time, quantities of money, quantities of supplies. So even if your problem doesn't come out and say it, you always want to include x is greater than or equal to 0 and y is greater than or equal to 0. Always, 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 because it's not going to be stated in the problem. But you have to put that constraint there so that when you are graphing, putting those constraints there is going to restrict your data to the first quadrant where all the numbers are positive. Okay, we don't need negative numbers, we need positive. So you yourself have to add those two constraints to every problem. So these constraints are all in standard form. So all I'm going to do is find the intercepts. So 2x equals 16. That means x is 8. So I have an x-intercept of 8, 0. 4y is less than or equal to 16. That means I have a y-intercept of 0, 4. So there's that line. Here it is. I graphed at 8, 0 and 0, 4. So, and you'll notice, guys, that my lines match the colors of my equation. And if that helps you do that, write each constraint in a different color and graph that line with that data, or with that color, excuse me. So like my first constraint is in green, and so I'm going to graph that with a green line. And that way I can tell what constraint goes with what equation. I always color code because it just makes it easier for me to see. All right, next constraint, 3x is basically equal to 9. That would be an x-intercept of 3, 0. And then y is 9, so that'd be 0, 9. So I'm going to graph 3, 0 and 0, 9 and connect the dots. Now you may be asking, do I have to extend my lines outside of the first quadrant? I'm going to say no. I just did it to show you that you can, but you don't have to. You can stop and go intercept to intercept. And then x is greater than or equal to 0. And then y is greater than or equal to 0. Now we need to talk about the shading. So it's got to be greater than the purple, greater than the red, but less than the blue and less than the green. So that's my shaded region right there, that little quadrilateral. Okay, so now we've graphed our system. We've found our feasible region. We have to shade. So this is everything you would do on a problem. Now let's find the 4 vertices. Sometimes you may only have 2, sometimes you may have 3, sometimes you may have 5. No limit on the amount of vertices. So I see I have one right here, one right here, one right here, and one right there. So I have 0, 0, 0, 4, 2, 3, and 3, 0. Those are my vertices. I'm now I am going to take these 4 vertices and I'm going to substitute them into my objective function. So if I put 0, 0, if I plug 0 in for x and 0 in for y, I make a profit of 0. If I plug 0 in for x and 4 for y, that gives me a profit of 60. If I plug 3 in for x and 0 in for y, I get a profit of $18. And then if I plug 2 in for x, 3 in for y, I get a profit of $57. So I take my corners, my vertices, and I plug them into the objective function. And I can see right here that the one that gives me the biggest profit is $60. Okay, $60. So the point is 0, 4, and my maximum profit is 60. Okay, let's look at the next slide. All right, last one. So here are the constraints. The members of the Cat Appreciation Club are on campus selling shirts and hats, and they want to maximize their profit. So they've given us the objective function, they've given us our constraints, and we just have to graph the constraints, shade, find the vertices, plug the vertices into the objective function, and then we're good. So pause the video, try it on your own, and then we'll see how we do. All right, so we've graphed it, we've named our vertices. I came up with a combination of 3 and 1. So if I sell 3 shirts and 1 hat, I'll maximize my profit and get a profit of $7. Okay, we didn't say it would be a well-run business. We just said that's what it is. So anyways, so if you have questions, please pop into tutoring and your teacher will be happy to work this problem with you if you don't understand. And that's it. You will now go on to complete worksheet 2.2, and that'll be due according to the due date set by your teacher. Have a great afternoon, or a great morning, or a great day, and we'll talk to you soon. Bye-bye.